Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. We're looking here at a short video, more integral concept questions. Basically we'll look at just two. The question is this: if a function is continuous and it has the interval from 0 to 2 f of x dx, and the value of that interval, here we're talking about areas below the curve, is equal to 6, then we have to evaluate this expression from lower limit 0 to pi over 2 f 2 sine theta cosine theta d theta. The fact that we're looking at here at interval from 0 to 2, and the fact that the function is continuous, it eliminates some type of functions like natural log x is not something which will fit over here, because you cannot do a natural log of 0. It wouldn't have 0 as a lower limit in terms of its domain, but something like sine x, e to the x, parabolics, cubics, various trigonometric functions, these will very well fit into these domains. But we don't have to get so specific here with regards to this question, because you can answer this question relatively easy. If you look at the first part, and it says this: from lower limit 0 to 2 we have f of x dx is equal to 6. If you look at this in a very general sense, and there's no specific function over here, you can easily move the f out like if it were a coefficient and rewrite everything like this: dx 6. Now here you can easily treat this as a basic polynomial, and you can do the antiderivative of that, and it's x squared over 2 using the n plus 1 divided by n plus 1 rule is equal to 6. We have a definite integral over here. You can take the 2 on the other side. We have f of x squared from 2 to the 0 is equal to 12. All you gotta do is put these in and the upper lower limits and the difference of the two. You will have f4 minus 0 is equal to 12, 4f is equal to 12, and f is equal to 3. We've developed a value for f, and this right here can fit very well over here. We can put a 3 over here. Now the second part of the question is not hard, because we now know f value is 3. This f value 3 can easily be pushed out here as a coefficient. You can rewrite everything here as 0 pi over 2. You have 2 sine theta cosine theta d theta. So this is where we are now. You can treat this as if it were part of each other, and you have a function and its derivative. You can easily do polynomial substitution. If u is equal to 2 sine theta, then du is equal to 2 cosine theta d theta, and you can solve for d theta, and you'll have du over 2 cosine theta. Your intervals will change with respect to what you have over here, and with this equation 2 times sine of 0 is just a 0, 2 times sine of 90 is a 2. So now everything becomes this: from 2 to the 0, u over here, and then cosine theta, and then du over 2 cosine theta. I'm just bringing the cosine theta here, and I'm bringing the 2 out here. These cancel out. You end up having 3 over 2, and 2, 0, you'll have u du. Again, this right here is very easy, because all we have to do is evaluate this. You'll do u squared over 2, and you have a 3 over 2 sitting outside from upper limit 2 to 0. These 2's can come together, and you'll have 3 over 4. U squared from 2 to the 0. Essentially all of this part right here with regards to the definite integration part of your antiderivative just leaves a 4. You have 3 over 4 times 4, and the 4's cancel out, and your answer is just a 3, and the answer would be right. So this question was not hard. It might have been tricky. Perhaps the most tricky part was to calculate the value of this f being 3. This last question is not hard. You have a derivative of a function which is continuous on an interval a comma b. We have to show that a function multiplied by its derivative over the interval a and b with a coefficient of 2, if you integrate that, it should equal to, in terms of its antiderivative undergoing definite integration, f of b whole square minus f of a whole square. And it's easy to do. I can refer you to that video I presented not long ago, an integral shortcut, where I show that anytime you have a function in the integrand along with its derivative, and you do the integration of that, you'll always end up with, as your antiderivative, f of x, the original function, squared over 2. Why? Because it'll always at some point undergo this procedure, conversion to f of u du, or you can say it will undergo this procedure, and then when you integrate it, you'll always get u squared over 2 plus c, and then the original function would come right over here, which is why anytime you have a function multiplied by its derivative, generally, and you do its definite integration or indefinite integration, you'll always get this as a rough template or a good template for your actual answer. Keeping that in mind, let's look at this question. How do you proceed over here? Well, you have a function and its derivative. It makes sense to use polynomial substitution. If u is equal to f of x, which here represents the function we're working with, then derivative of u must equal to the derivative of this f of x dx, and you solve for dx is equal to du over this derivative of x. You know this prime means derivative of that function. You have to create new intervals because we actually have intervals presented here. u1 is equal to, everything is going with regards to this. You end up putting the a in there, you get f of a. u2 is equal to, you put the b in here and you get f of b. And now you can easily recreate a new expression with this substitution. You have a 2 sitting outside, which is fine. Then you have a lower limit of f of a and an upper limit of f of b. You have f of x, which is substituted by u, and then you have this derivative of x, and then you have du over f prime x, or the derivative of your original function. These cancel out. You end up having f of b as the upper limit, f of a of the lower limit, 2 sitting outside, u du. This is exactly what I was talking about. When you take this 2, you get u squared over 2. You have this 2 sitting out, and then you have this interval over here, f of b and f of a. The 2's cancel out, you have u squared, and you integrate these easily. You get f of b whole square minus f of a whole square. That gives you your answer that you were looking for all along. The difference of the two limits placed into your antiderivative gives you exactly what you were trying to show. An integrand that is composed of a function and its derivative are very easy to handle because you will always get the type of format, so long as there's no isolated constant involved, where you'll have the original function squared divided by 2 as your antiderivative. I again refer you to that video. An integral shortcut is the name of that video, where I'm talking about something like this. But that's all I wanted to present in this video. Hopefully you enjoyed it. Thank you. Have a nice day.